All right. Hello, everyone, and welcome back. We're continuing on with MCT4C, the Math for College Technologies,
Recording in
and
progress.
we're going to be today looking at beginning our journey into polynomials, which we're going to spend quite a bit of time on that. And so, uh, let's go ahead and get started here. Share the screen. Yes. Okay. So today I have two tabs open for us. I've got my Desmos calculator and I've got my Desmos graph. We're going to end up using both today. So that's why I have them both open for us and we're going to keep this a bit longer. And so we're at the end of unit one. And we are looking at polynomials. This is a three-part lesson. So we're going to finish up on Tuesday and then have a review of topics on Wednesday. And then after in unit two, we're going to be studying more polynomials. Specifically, we're going to have with an eye towards being able to factor them. But today I thought it'd be a good idea to offer up a review of topics, just because if you kind of go through the lesson, there's a lot of material there and a lot of assumptions made with respect to understanding the material and like past knowledge. So I thought it'd be worthwhile to review linear and quadratic functions and go from there. So we're looking at polynomial functions, specifically today, linear and quadratic. And the concepts we're going to be studying today will be the degree and identification of polynomial functions, linear polynomials, quadratic and simplifying polynomial expressions, as well as sketching linear and quadratic functions. And I say sketch because you can't graph all of these with the table of values, but at times it's easier to provide like a quick sketch. So I'll have a show you the difference between these and what they look like. In general, you're kind of got the lesson is if you're able to analyze and understand linear and quadratic polynomials, and as well if you're able to simplify polynomial expressions, that's how you know you're going to be good to move on from this lesson. So with respect to the classification of a polynomial, zoom out a bit, sorry. A polynomial expression is a series of terms in which each term is the product of a constant in the power of x that has a whole number as the exponent. And so the following are all examples of polynomials. So you can see here we've got y equals 3x minus 1, f of x equals negative 4x plus 3. Do note that I could have written that f of x function merely as y is equal to negative 4x plus 3. I just wanted you to get used to the notation that f of x does exist, and we're going to be using it on occasion. So the first two here are written are just written in y equals mx plus b form. But for the next one here, we have y is equal to 4 in brackets x minus 1. This is the factored form of a linear equation. Afterwards, we have y equals 4x squared plus x minus 2. F of x equals x squared minus 2. And y is equal to x minus 3 times x plus 3. Ideally, we should be able to with what later lessons we're going to be looking at, is being able to transform a quadratic into the form y equals x minus 3 times x plus 2. Previously, in previous courses, you also studied the y is equal to 4 times x minus 1 squared plus 1. This form is what is known as vertex form, because you get the vertex from here. This y equals x minus 3 times x plus 2 is what we call factored form, and we're going to be spending more time on that. And for this first one, y equals 4x squared plus x minus 2, this is what we call standard form. So previously, these are all things that you have already studied and looked at, but typically I want to review factored form kind of throughout this. So these were your standard linear and quadratic polynomials. They can get larger though. So y equals 5x to the power of 3 plus 4x minus 2. This is actually what we call a cubic polynomial. And it's called it's a cubic because the biggest x value, or I should say The greatest exponent that appears in this particular equation is a power of 3, and there's no multiplication. If you look at the fifth one here, we've got, the fourth one down, y equals 5 times x minus 4 times x plus 1 times x minus 2 times x plus 4 times x minus 8. This is also a polynomial. It's quite lengthy. But fundamentally, the techniques we're going to use to analyze this are exactly the same as the quadratic one. It's just that it's longer. This polynomial happens to be a degree 5 function, and we call that a quintic. For our course, we typically don't go above degree 4, but I just wanted to show you that this exists. And this last one here is y is equal to x minus 5 times x plus 1 plus 2x squared minus 3. This will also be a polynomial. And in fact, specifically, this one is only a quadratic. Okay, since if you were to expand or multiply out the x minus 5 times x plus 1, that forms a quadratic, and then you're adding on another quadratic. Hence, the resulting expression is a quadratic. So the following here are not polynomial functions. And these all have names, which I'll go ahead and name for you. Some of these you've already seen. F of x equals 10 times 2 to the power of x. We spent some time studying equations that look like this. This one was called an exponential. And the reason why it's exponential is because the variable is an exponent. This next one we've pretty much never studied in this course, but it does exist, and I'll just make mention of it. Y equals 2 over x minus 1. This is called a rational function. It's called rational because, we think about it as in terms of a fraction, but essentially we start seeing x's in the denominator. In lesson 10, we're going to study this y equals sin x. You might be thinking, is this the same sin and cos or sine and cos that we saw from trigonometry? It is actually. So this is what we call a sinusoidal function. Or some people call this the trigonometric function. That's fine as well. Y equals the square root of 2x minus 3. You're like, oh, the square roots have ones too? Sure they do. This one's called a radical function. We have this y equals log x. We just saw that in the last couple of lessons. This was called a logarithmic function. And if we've got x cubed y is equal to x cubed minus 2x squared plus x to the power of negative 1, this is what we call a combination function. It's combined of 2 or more other functions. So specifically, this is both a polynomial and a rational function. You might think, hey, look, this looks like a polynomial because there's these positive exponents there. But then you have this negative one that's kind of tucked in there as well. So it ends up being a combination of them. And so the degree of a polynomial function in one variable, because you can actually graph these things with more than one variable, but we're not going to touch those in this course, is the greatest exponent of the variable on any one term. And so we're going to consider the following here. Y is equal to x to the power of 3 plus 7x to the power of 2 minus 2x minus 1. So here, the largest exponent is this x to the power of 3 term. And so here we would say that this is a degree 3. Okay? And the reason why we care about this is that since there's this x to the power of 3 term, that means it's not going to behave like a quadratic. It's going to behave like the next one up, which is what we call a cubic. But again, the cubic we're going to study on Monday, but I'm just introducing the terminology now for you. This next one here, we've got y is equal to, in brackets, x minus 2 times x plus 5. This one is going to be a degree 2. Why is that the case? Well, if you were to multiply out what this top one looks like, so x minus 2 times x plus 1, so we'll use FOIL for the moment. X times x is x squared. X times 5 is 5x. Negative 2 times x is negative 2x, and negative 2 times 5 is negative 10. This will then simplify down to x squared plus 3x minus 10. The largest single term in here that appears is this x to the power of 2, which is how we know it's a degree 2. That's going to come in handy when we look at some of these larger terms down here because we don't really want to expand this out. We would then just say, oh, how many x's are multiplied together? We can say, oh, it's x times x is x squared, so it's a degree 2. So, okay. So we're going to, in example 1, determine the degree of the following polynomials. And again, if you're watching this on YouTube, I would encourage you at this moment to pause the video, try these out for yourselves and see how you did. Okay, so let's go through these. We first one here, we've got y equals 3x minus 1. So the greatest variable here is just this x, but it's a degree 1. Because remember, we put a little imaginary 1 there. Well, not imaginary, it's always there, but we just neglect to write it. But that's a linear expression, so it's degree 1. B, y is equal to 3 bracket x plus 2. This one also is going to be a degree 1. Because again, if you were to multiply this out, the biggest term in there is just going to be a 3x. Hence, we can say it's a degree 1 polynomial. For letter C, we have y is equal to 4x squared minus 3x plus 1. This is going to be a degree 2. Because again, the largest term that appears there is an x to the power of 2. Letter D, we have y is equal to 5x to the power of 4 plus x to the power of 3 plus 2x. So we can see the biggest term here is this, or the largest term is this x to the power of 4. And so we would say that this is a degree 4. This has a name. So we call these a quartic function or relation, whatever. So you know how we call degree 2 quadratic, degree 3 is called cubic, degree 4 is called quartic. And we study up to primarily degree 4 functions. But the techniques that I show you can be applied to any degree you would like. It just takes way more work the larger the degree. Okay. Letter E, we have y is equal to x minus 2 times x plus 1. So if you were to multiply out these x's, you would end up with a degree 2 polynomial. And for f, we have y is equal to x times x minus 1 multiplied by the quantity x plus 2 multiplied by the quantity x minus 3. So if you were to multiply out all of these x's, x times x would be some sort of x cubed term plus some stuff. But importantly, the largest term that will appear here is a degree 3, this x to the power of 3. So we would say the degree on this is going to be 3. Letter G, we have y is equal to 7x to the power of 3 minus 4x plus 9x to the power of 10. So here they happen to go, the order of this is out of order. Typically, you want to write this with the greatest degree go first. So we write this as y is equal to 9x to the power of 10 plus 7x to the power of 3 minus 4x. So we start with the biggest value of x, which is x to the power of 10, and just work our way down. It's polite to write it this way so we don't somehow confuse ourselves. But in this case, you can see that the greatest term is a degree 10, which is this 9x to the power of 10. And so we would say that this degree is going to be a 10. The trickiest one is this h value, h, which is just y equals 6. So the question I'm going to ask you is, do you see any x values in there? The answer to that question is no. So it's a degree 0. And so you might be saying, your intuition is saying, well, that doesn't seem right. Well, keep in mind, you can add 0x to this. But if you add 0x, it just goes away. And so there's actually no x value there. So if you end up with just a constant, which is what this is degree 0. Okay. And the purpose is, and you might be wondering, like, okay, this seems fairly reasonably straightforward, I suppose. Why do I need to be able to identify the degree of these polynomials? Well, because later on Tuesday, we're actually going to sketch what these things look like. And in order to sketch them accurately, we need to be able to identify what the degree is. Because if it's a quadratic, cubic, or it's a quartic, we should be aware of what those are. So the main kind of polynomials we're going to be looking at, well, for today, are going to be linear and quadratic, which was the degree 1 and degree 2, as well as in the future, cubic and quartic, which are going to be degree 1 and, oh, sorry, not degree 1, degree 3 and degree 4. And again, what I will teach you about cubic and quartic, you can extend that to higher degrees as well, and they all have names all the way up. Okay, so let's have a look at these things. You can graph these on Desmos. So on the right here, I'm not going to read this yet. I plotted two curves. I have this red line. Maybe perhaps I should put it in red. This is y is equal to 2x plus 4. You can type this in for yourself on Desmos. So desmos.com/graphing calculator. If you've used it before, great. If you haven't, basically it's a much newer version of like old TI-83 graphing calculators. And it's fairly intuitive, like actually on a mobile device makes the most sense. So I'm on like a tablet right now. But here, I can just type into the equation, open up my keyboard and go y is equal to 2x plus 4. And if you do this, I end up getting the exact same line. And so I can zoom in, zoom out, and it gives me an accurate representation of what this graph looks like. Suppose instead I wanted to graph this blue quadratic at the bottom here. This y is equal to, and again, I just open up my keyboard. Y is equal to negative x to the power of 2 plus sine 9x minus 14. And if you do that, you get the other quadratic here. Sorry, you get the quadratic here. And if you click on the quadratic, it'll give you neat information. In this case, you end up getting the vertex, but it also tell you the x-intercepts, which is a fairly useful property that we actually do care about. So at this point here, if you haven't used Desmos before, I would encourage you to pause the video here and again, start playing with the technology. Make sure you're able to type this in. And the other thing you want to do is you can also, if you hold, like pinch your two fingers on the X or Y axis, you can shrink the scale. Okay, I'm just moving it in and out. And if you just pinch your fingers together closer or together, you can zoom in and out on the graph as well. And if things appear to be going badly, just make sure just to reset the page. Okay, because sometimes these things happen. All right, let's continue on. So linear functions have the form y equals mx plus b. And keep in mind, we can also write this as f of x equals mx plus b. Just remember that we tend to interchange f of x and y of x. F of x and y equals. And these things have a degree of 1. So as long as a linear function is in the form y equals mx plus b, b is what we call the y-intercept, and m is the slope. So if you notice here, there's a plus 4. That means this is where it crosses the y-axis. So this is my x-axis, this is my y-axis. It'll cross here at 4 in the case of y equals 2x plus 4. Okay. M is the slope, which tells you how steep the line is. So here in this one, the slope is equal to 2, but we can write anything as 2 over 1, which means if we start at, say, this point here, I'll zoom in a bit to make it easier. We can go up 2 units and then over 1 unit. And this pattern repeats. So 1, 2, so we can go 2 up and 1 over. Okay. Quadratic functions have the form f of x is equal to ax squared plus bx plus c. And note that again, this is the y is equal to ax squared plus bx plus c. And these have a degree of 2. As long as a quadratic function is in the form y equals ax squared plus bx plus c, a tells you whether it's going to open upwards or downwards, and c is the y-intercept. So in general here, if you notice, this a value is equal to -1. So this will open downward. But in general, if a is greater than 0, this means it'll open upward. And if a is less than 0, this means it'll open downward. And c is going to be the y-intercept. So in this case here, can't quite get to it, but the y-intercept would be down here at -14 if the graph were to continue that much further. You can see on the left here that if I click, there's my y-intercept of -14 down at the bottom. So far so good. These are general properties. Again, if this is a review for you, fantastic. If this is new, like again, feel free to review this, like replay this part of the video, just make sure you kind of understand roughly what's going on. And so what does the role of k do? So here we're talking about functions of the form, say y is equal to k times x minus some, let's not use c, let's do minus some d value. So k primarily is going to be, for us, can be the slope. So if k is negative, so for example here, we have this, the case of k being equal to -3, your line will go downwards. And specifically, there's new notation for us. You might be thinking, is the word decreases just here because of an English thing? No, actually, it's a legitimate thing. A function is decreasing if you can trace your finger from left to right and it goes downwards. Similarly, a function is increasing when you trace your finger from left to right, the function is increasing. So this is when, so a function, so here as a serious note, you can tell if a function is increasing or decreasing when read from left to right. So again, if you're looking at the left and it goes down, it decreases. And if you're looking, and if it goes up, it increases. And again, you just trace your finger along, kind of see what it looks like. Linear relations can be sketched using a table of values or using the slope and y-intercept. Both are okay. So something, hopefully that's a review for you, but if not, that's okay. Is we're going to sketch the following. So if we have y is equal to 2x minus 1, you can sketch this either using the slope and the y-intercept or table of values. I'll show you both and plot the solution and then have Desmos confirm this is the case. Okay, so if it's y equals 2x minus 1, the slope, m, is equal to 2. And remember, this means it's equal to 2 over 1, because slope, by definition, is rise over run. The y-intercept is going to be -1. So on the y-axis, we start at -1. So there it is here. And now from here, we want to go up 2 units and forward 1. Up 2 units, and then forward 1 unit. And so you can see this pattern begin to form. You can also go backwards as well, but at the end of it, you should see it should be forming some sort of straight line. And from here, you do your best to connect this. Ideally with the ruler, I don't have such technology with me, so I'll settle for just using a straight edge. Sorry, to try to freehand it. And then afterwards, what you want to do is be polite and make sure to label what this is. Now, if you don't feel comfortable using the slope and y-intercept, completely reasonable. What you can do instead is plot this as a series using a table of values. And so wherever you see an x, you can go ahead and, so we want to substitute just regular values, -2, -1, 0, 1, 2. So we want to type in 2 times -2 minus 1, 2 times -1 minus 1, 2 times 0 minus 1, 2 times 1 minus 1, and 2 times 2 minus 1. So I like to start from the bottom because it's easier. 2 times 2 is 4, minus 1 is 3. 2 times 1 is 2, minus 1 is 1. And we can go backwards and fill out this chart. So there it is. And so that gives us a series of ordered pairs. And if you notice on the graph here, our first point is -2, -5, which is going to be right there. The next one is going to be -1, -3, which is right there. The next one is 0, -1, which is here, and so forth. So you can see that the table of values gives us 5 points to work with, and then we can connect that with a straight line, and we get the exact same answer. So feel free to sketch linear relations however you would like. If you want to use a table of values, so be it. If you want to use the slope and y-intercept, so be it. Using Desmos here, we can also check to make sure we did this correct. So if I type in y is equal to 2x minus 1, close that, we end up getting the exact same function. So I got to zoom in a tiny bit here. If I click on the wrench, I'm going to have my x-axis go up by 1, my y-axis, the step also go up by 1, and I can just get rid of these minor grid lines, and I get the exact same graph. So you can see here there was 0, -1. Down here we could see this is the point -1, -3, and so forth. Okay. I'm just refreshing because I got rid of some settings that I actually like in there. Okay. So the zeros of a polynomial functions in factored form. So for the zeros of polynomial functions in factored form, the zero or x-intercepts of a linear function f of s is s, and f of x equals k times x minus s. So this just means, so the zeros refers to where we cross the x-axis. So zeros equals the x-intercepts, which equals the quote where the graph crosses the x-axis. Okay. For linear function, if they happen to look like this, you can get the x-intercept. Most people don't use the x-intercept form of the linear polynomial since there's no real need to. But however, we do use the factored form is what this is called. So the zero of a quadratic function, y, are s and t in this one. So this, or what we said earlier, was called factored function. In general, we can say a quadratic relation can have 0, 1, or 2 zeros. So meaning that this quadratic will not intercept the x-axis at all. It'll intersect in 1 point, or it'll intersect in 2 points. So you can hear this has 0 zeros. This one has 1 0. And this red one has 2 zeros. Okay, and that's it. So they could be upside down, but you can at most you can have 2. At the very least, you can have 0. And in general, I stated this earlier, the book uses different terminology. You might be familiar with A, and I think did I use A up here? Yeah, I used A up there. But the book did K because they're trying to group in cubic and quartic later, whereas I'm just focusing on linear and quadratic for now. So in general, if your value of K is greater than 0, they will open up. So for these ones here, all of these quadratics, they all have a K value greater than 0. So like K could be 1, 2, 3, 0.04, and so forth. If I had to look at this, it looks like K is equal to 1 for all of these. Okay. So we can use the value of K and the zeros of a quadratic to sketch functions, not to graph them, to sketch them. Okay. And so, for example, 3, we're going to provide a graph and a sketch of the above quadratic relation. Okay, so we're going to do a graph first because that's the normal thing to do. And again, to do a graph, we try to choose values around the x-intercepts. So here, these values were chosen purposely. So we can choose the standard values -1, 0, 1, and 2, because here we have an x-intercept of -1, and here we have an x-intercept of 2. For now, please do at this point is get the y values by typing each of these in. So wherever we see an x, we can replace it with -2. So this will be -2 plus 1 times -2 minus 2. The next one would be -1 plus 1 times -1 minus 1. The next one will be 0 plus 1 times 0 minus 2. The next one will be 1 plus 1 times 1 minus 2. And the last one here will be 2 plus 1 times 2 minus 2. So a couple of these you might have spotted look pretty easy, but again, we can use a calculator as if we're not feeling too confident with this. So if I type in -2 plus 1 multiplied by -2 minus 2. And so we can see the answer to this is going to be 4. And so again, I'm using the Desmos scientific calculator and the Desmos graphing calculator. You can find these both by just typing in Google, Desmos scientific calculator, Desmos graphing calculator. Okay. The next one here, we have, instead of -2, we can sub in -1, and we can see we get a 0 here. The next one, we type in a 0. And you can see why I like using the Desmos calculator. I don't have to type in all those brackets again. I can actually just use, like retype in place of these answers. Instead of 0, we can put in 1. So as it turns out, 1 plus 1 times 1 minus 2 is going to give us -2. And lastly, if I try to type in a 0 here, we're going to have 2 plus 1 times 2 minus 0, which is 0. Values, so -2 comma 4 is up here, -1 comma 0 is here, 0 comma -2 is here, 1 comma -2 is here, and 2 comma 0 is here. I would hope, and you might be thinking a little bit suspiciously or accurately, you might be saying, I feel like 3 comma 4 looks like a point. And you'd be accurate. That is indeed the case. So if we typed in a 3 down here, you would expect to get an answer of 4. You can verify that using a calculator if you would like. Okay. Now, I'm going to sketch this badly at first, intentionally. So if we just try to connect the dots here, we get a graph that looks like this. And you might be thinking that, hey, this bottom portion appears to be a bit off, and you'd be correct. So we know from our previous studies of quadratics that it kind of dips down a bit more than you would expect, which is the case. And so we get our graph looking like this. And so if I were to graph this on the Desmos graphing calculator, y is equal to x plus 1 times x minus 2. Here is what the graph looks like. So there's our zeros. Now, as it turns out, it has a vertex down there of 0.5 comma negative 2.5. But there's those 3 points that we spoke of. Okay. So how do I sketch this instead? Since this is well, I was going to say this is a beautiful detailed graph, but I think I could say is that this is a detailed graph. The beauty I leave to you. Hopefully you guys will accept that. So for a sketch, we need to know what happens here. So here, the a value is equal to 1, or I should say, we use a k for this, I think. Yeah, we use k. So we'll use the correct terminology. So k is equal to 1. So this opens upward. K is equal to 1. So therefore it opens upward. And for the x-intercepts, you set each of the factors equal to 0. So you want to solve the equation 0 is equal to x plus 1 times x minus 2. And so we have 0 is equal to x plus 1 and 0 is x minus 2. Solving these equations has x equals negative 1 and x equals 2. So our x-intercepts here are negative 1 and 2. So if you're able to just list them off right away, you should do that. So to get the sketch portion, we draw on a little Cartesian plane, like so. We plot in our x-intercept. So there's one here at negative 1. Here's one over here at 2. And since we know it opens upwards, we know that the graph of this thing must look something like this. And then afterwards, all we do is label our graph. So here's what they look like. So this is a reasonable sketch of what this looks like. If you want to be a bit more detailed, you could also plot in the x-intercept. And remember to get the you can also plot in the y-intercept. And for the y-intercept, remember you want to be typing in f of 0, which in our case is going to be 0 plus 1 times 0 minus 2, which is going to give us negative 2. Okay, and that's a reasonable sketch. Okay, the reason why that I'm showing you is like, well, why did we, this is way less work than graphing this. It is. And the reason why sketches are important is that in the case of a quadratic, it's not too much of an ask to do a graph of this. But if we want to end up graphing cubic and quartic functions, using a table of values is a ton of work. And so it's actually a lot more efficient to actually sketch what those things look like. But again, we'll leave that for later. Okay, we're going to sketch the following quadratic relation. So I've got here 4 of them. So let's go through these pretty quickly. And so all we need to know is the k value. So this is k equals 2. So this is going to open upward. This has x-intercepts of 3 and negative 1. Okay. So essentially you take the opposite because the x-intercepts are asking what causes this thing to equal 0. And so in terms of a sketch of what this looks like, oh, I'm on a tablet. That was such a bad line. There you go. So we go to negative 1, which is over here. We go to 3, which is over here. And we know that it's going to open roughly like this. And so this is a reasonable sketch of what this looks like. And again, your sketch doesn't need to be perfect. Like mine leaves much to be desired, but it's at least reasonably close. Okay, so for b, we have y is equal to negative, multiplied by x plus 4 times x plus 7. So here we have a k value equal to negative 1. So we know that this will open downward. Okay. And so we have x-intercepts of -4 and -7. So on our graph, out here to -4, -7, and it opens downward. So it is. And again, this is a reasonable sketch of what this looks like. Okay. What about y is equal to 3x times x minus 2? So here we have a k value equal to 3. So this will open upward. And for x-intercepts, it has the trickiest one of them all. It's here. We actually have an x-intercept at 0. So if you notice here, this 3x isn't plus or minus anything. It's just a 3x. So that means you got an x-intercept of 0, and we have 2. I would say that for students, the one that causes the most amount of trouble actually is an x-intercept of 0 because it's somehow too easy, but I do understand. Okay, so we have a x-intercept of 0. There it is. We also have one at 2. There it is. And it opens upwards. So it does. And so there's our graph. Last one here, we have a k is equal to -2. So this will open downward. And we only have one x-intercept. I'm actually going to write this neatly because I'm going to write a new word for you afterwards. So here we have an x-intercept of just 4. But I'm going to leave some space there for the moment. Okay, so here we have an x-intercept of just 4, and it opens downward. So that means it has to do this. And we saw this example earlier when we were having a look at the case of 1, 0. That means it kind of just bounces off the x-axis. So that's what's happening here. Now, we're going to study this on Monday, but I'll give you a little bit of a prelude. If you have an x-intercept like this, and it's got a power 2 up here, we say that this has multiplicity 2. Sometimes this is also called order 2. And so what happens on the graph is that this causes a bounce, which is what this has. And again, this is a little prelude to what we're going to be looking at later, but just realize that here, even though it just sits on the x-axis, we didn't think much of it, but actually it does have a special purpose, which we'll study later. Okay? All right. Last thing we're going to look at is we're going to be looking at expanding and simplifying. And we're going to express each answer in standard form. And we're going to start at the easiest one and work our way down to the hardest one. So for question letter A, I should mention standard form means that it's going to be something like y is equal to ax squared plus bx plus c. So the largest degree goes first, then the next largest degree goes second, then the constant goes at the end. Okay, if this was a cubic or a quartic, we might say that this is ax to the power of 4 plus bx to the power of 3 plus cx to the power of 2 plus dx plus c. But in general, you start with the biggest degree and you work your way down. So for A, we have the all-powerful y is equal to 2 minus 3x. So the position of those is backwards. So we can rewrite this as, in fact, I think I want to work in red for these. Y is equal to negative 3x plus 2. Okay, so be it. For letter B, we have y is equal to 3 multiplied by the quantity x minus 4. So we just want to take this 3 and multiply it onto both terms inside the bracket. So 3 times x is going to be 3x. 3 times negative 4 is going to be negative 12. Okay, sounds good so far. What about C? Well, that's going to be y is equal to negative 4 times 2x plus 1. So this will be negative 4 times 2, which is going to be negative x of the x variety, or negative 8 of the x variety. Negative 4 times 1 is going to be negative 4. Letter D, we have y is equal to 4 minus x squared plus 3x. Again, the order of these is wrong. So this should be negative x squared goes first, plus 3x, and plus 4. Okay. So E is an interest. So here from here, in school and such, like there shouldn't be too much disagreement about which one you learned. I think most people are quite happy at that. From E onwards, there is some disagreement how you might have been taught how to do these things. Drag for new page. Can I do that? Yeah. So I'm going to take this. I'm going to show what I think most people have normally solved this. So what most people would do to solve this one, and we're looking at y is equal to the quantity x plus 4 in brackets multiplied by x minus 3, also in brackets. So it's what we call two binomials multiplied by each other. You would take the x term and multiply it onto x, take the x term and then multiply it onto negative 3. Afterwards, take this 4 and multiply it onto x, and take this 4 and multiply it on negative 3. So the acronym for this is called FOIL, and it stands for first term outside, inside, last. But the way I prefer you think about this is you want to take this first x, multiply it by the second bracket, then take this 4 and multiply it by the second bracket. So at any rate, first term will be x times x, which is x squared. X times negative 3 is negative 3x. 4 times x is 4x. 4 times negative 3 is negative 12. At this point here, we have two terms that we call like terms, so we want to just combine those together. And so we end up with y is equal to x squared plus x minus 12. So I got us an extra page down here. So I want to show you two other ways you could solve this or simplify that down. So if you have y is equal to, what was it again? X plus 4 times x minus 3. You could do what we call the array method. So what you would do, and again, if you've never seen this before and you're like, can I just FOIL instead? You absolutely can. The first term here is an x plus 4. The second term here is an x and a negative 3. And you would fill in, and what we want to be doing is multiplying these. So x times x is going to give us x squared. X times 4 is 4x. Negative 3 times x is negative 3x. Negative 3 times 4 is negative 12. From here, you combine all of the terms together. So this is x squared plus 4x minus 3x minus 12, which gives us a final solution of x squared plus x minus 12. So this is called the array, sometimes called the area method, if you learned about this in elementary school, because you can do this with 2 and 3 digit numbers as well. The other way I want to show you how to deal with this, and I'm going to cheat and actually color code this one for us. This is called using the distributive property. Or for those of you from Alberta, this is actually what they do in Alberta. So we will honor them by calling it the Alberta method. And so essentially what they do is the following. And if I had to pick a method I actually like, it's this one the most. So they take your x plus 4 and your x minus 3. And so the shorthand I was using was I said, hey, we're going to take our x value and multiply it by the second bracket. And then we're going to take the 4 and multiply it by the second bracket. And so this is FOIL, but we're showing an extra step. And so when we go ahead and solve this, we end up getting x times x is x squared, x times negative 3 is negative 3x, 4 times x is 4x, and 4 times negative 3 is negative 12. And combining this, we end up getting the exact same solution. So for teaching purposes, I actually like showing you the distributive property because then you can, because later we're going to factor these things and we're going to factor difficult ones. The being seen this method actually makes sense because if we want to go that's fine with me. Okay, let's continue on. We have y is equal to 4x times the quantity x plus 5. So we want to take 4x times x and 4x times 5. And so 4x times x is going to be 4x squared. 4x times 5 is just going to be 20x. Okay, g's the longest of these. So we now have y is equal to, now we've got a 3 out the front, 2x minus 1 times in brackets x plus 5. So again, what I would recommend is we actually just deal with the inside portion first and then multiply by 3 afterwards. So we're going to take y is equal to 3, leave the bracket. 2x times x is going to give us 2x squared. 2x multiplied by 5 is going to give us positive 10x. Negative 1 times x is going to give us negative x, and negative 1 times 5 is going to give us negative 5. We're going to simplify our inside term, so we're going to write y equals 3. That doesn't change. The 2x squared. 10x minus x is going to give us 9x minus 5. And then last thing we do is go ahead and multiply out the 3 onto all of the terms on the inside. So 3 times 2x squared will give us 6x squared. 3 multiplied by negative 9 will give us negative 27x. And 3 times negative 5 will give us negative 15. You could have multiplied the 3 out first. So you could take 3 and multiply it by 2x and then take it by negative 1. I find this leads to more difficult calculations, uses a bit more brain power, and I prefer not to do that. So I try to keep it as simple as possible until the end. All right, last but not leastly, we have here y is equal to 3 times x minus 4 squared. So remember that little 2 means that there are 2 of those. So it'll be x minus 4 times x minus 4. And so we multiply this out. X times x is going to be x squared. X times negative 4 is negative 4x. Negative 4 times x is negative 4x. And negative 4 times negative 4 is 16. We're going to combine our terms so that 3 stays the same. And we still have our x squared. Negative 4x minus 4x will be minus 8x plus a 16 at the end. And then we just multiply out the 3 onto all terms on the inside. So 3 times x squared will be 3x squared. 3 times negative 8 will be negative 24 of the x variety. And 3 times 16 will be 48. Okay, so so this will take care of parts of the key questions from the ILC. But I want on Monday, we're going to be expanding our understanding of how to simplify more complicated expressions. So instead of having 2 binomials, maybe perhaps we have 3 or 4 binomials to worry about, as well as looking at more complicated sketches of these. And in general, just kind of building up our understanding of this. But for now, I think that's a good place to stop, and I'll see all of you next time. Goodbye for now.